Let me start with the introduction of myself. I'm originally from Wrocław. I work here at the Department of Physics and Astronomy, and today I will present some kind of not usual stuff for myself. So please be aware that I'm doing this for like second or third time to talk about this particular topic, and the reason for that is that the topic is new, also for me, and yeah. So let's. Let's move on. And what is this about? So what I'm working on every day is the fluid dynamics stuff. So I'm a computational physicist working with fluid dynamics, and what you see here is the one of the results from the very past. When I was a PhD student, I was working with computational code for solving Navier-Stokes equations problems, which was created in our lab. So we were writing our own software, basically programming in C++. What you see here is the fluid flow through the over shape of a car, which is generating vortices, and all of this you see here is the result of the boundary conditions that are applied, and the equations that we are solving are Navier-Stokes. And yeah, why do I show this? Because when I was a PhD student, I was spending a lot of time on writing the software to calculate these flows. Of course, there are some libraries, there is a lot of software that you can use which is ready for use. There are people who already wrote something. But this is now changing. And the whole talk is about how this changes for me from my perspective. And today we are, of course, doing some three-dimensional fluid flows. We are dealing with porous medium. What you see here is result from the recent work of Sakrish, who is now participating in this seminar as well. And she is working with the open source code um, for the solution of Navier-Stokes equations, and this is finite volume based method, which is written as an open library, open form. And I'm showing this for you to show you the origin of all the thoughts that I have in my mind now. And the reason I'm here and I'm trying to give you this talk is that I have a lot of experience with programming. So I'm originally programmer. I was always working with assembler, C, C++, Python, JavaScript. I'm teaching programming. I also wrote a book about computer simulations and about C++. And this is not to show off. This is more to settle myself, because I want to cover some message today, and yeah, and the message is quite big. So I think for you to understand that I know a bit about programming. Okay, and now 2025. What I was showing you before was before the 2025. So all those results, the fluid flows, the lattice-Boltzmann implementations that you have seen, this flow over car was lattice-Boltzmann, I didn't mention that, was before 2025. And I think this slide is appropriate because something has happened. And this is related to the development of AI, of course. And this is DeepSeek. So Chinese company has created a AI model. Usually we call those models chats. This is a bit deeper, but it's not it's not the subject of this talk. But what they created was, was what they released in 2025 in January. So it's not even a year before. Was a language model that has a capability of so-called deep thinking. Okay, so from my perspective, that was, as for everyone, just a kind of interesting thing that happened. Okay, I opened it, I started to chat a little bit. Of course, beforehand, in 2024, we were all chatting with ChatGPT, and so all this funny stuff that we were doing, like write the story, tell me a story, a fairy tale, yeah, kind of stuff like this, everyone was doing because it was everywhere in each newspaper. But in January, when this Chinese company has thrown to the market DeepSeek R3, the model with deep thinking capabilities, it changed a lot. And so immediately many people jumped in, tried something just to see what this DeepSeek can do with the knowledge that they had. And so my initial idea was, okay, I will try to use DeepSeek to the work that I'm doing every day. And yeah, so now I will introduce the talk. What this lecture will not cover. I will not talk about how language models are working, because I'm not a specialist. I'm the user. I will be talking about the language models from the user perspective. I will not cover how neural network works. However, this we can talk about a bit maybe later, but it's not about this, not today. I will not talk about theory. So what this talk will be about? This will be about practice. And I spent quite a lot of time, so like 7 months, on working with modeling with language models. The idea was that when in January I jumped into the DeepSeek, I recognized that this is an ocean of possibilities. Sometimes you have this feeling when you start with some new model or a new model. I think I'm talking about the model in physics, in science itself, that you feel like you open, I wouldn't say Pandora box, but something like this in a positive way, that basically you can do a lot more that you were able to do beforehand. And that was something that forced me to push a little bit of this subject for myself from my own perspective. And my perspective was always practical. So whenever I tried to understand something, I had to work with it. So that's the idea that was there. And yeah, I spent 7 months. That mostly evenings, because for evenings are like for digging the stuff, deeper and deeper, and I was working with that like this. So that was my first. DeepSeek. That was my first DeepSeek guess. I was trying to write a program that simulates lattice-Boltzmann method. And that was my initial guess how to do it. Okay, I was not okay. This is Polish, so for everyone that is not Polish, I'm sorry, but this particular prompt, we call this prompt like description of the problem to be solved by a language model. This particular prompt is in Polish because this is how I did it initially. I just opened DeepSeek and I've thrown this. And so let me explain what is there. So this is a description of a program that the idea was that the program is solving a simple fluid flow problem in a JavaScript language. JavaScript because this is the simplest to copy and basically open in web browser to run and to see the result. The problem to be solved is a Poisson flow. The method to be used is lattice-Boltzmann, and the idea was that we will have the results of this model of a fluid flow in a form of visualization of the velocity field, where the velocity is coded as a magnitude so the magnitude of velocity is coding the color. So black is the lowest and the white is the highest velocity. And I asked that the system is periodic in the x direction and no slip condition. So in Polish bez poślizgu on the top and bottom wall. And the gravity should be accelerating the flow. Now, this simple prompt is showing the initial guess how to do it, and it is okay. It is when you read it, you immediately recognize that this is kind of not really complete. if I asked someone who didn't know about lattice Boltzmann at all, he or she would not be able to write down the program for it, because LBM is the shortcut, because I already knew from my knowledge that LBM is lattice Boltzmann. So if you give a prompt like this to a person on the street and ask to do something, he or she will not be able to do anything, because one has to have some knowledge and know how the lattice Boltzmann, what lattice Boltzmann is doing, and what are the no slip conditions, and so on and so on. And but if you do give the prompt like this to a good student that is already after some courses on fluid dynamics, on programming, and so on, he will be able to do it because he will connect the dots. Okay, so LBM, Poisson flow, JavaScript, periodic boundaries, and everything between will be filled by this person. And now, so of course, the first question is whether those language models like that are able to connect the dots and fill the program like that by the content. And the result, of course, you can imagine, because that would be no following up slides if this would not work, that it worked pretty well. And this is how it looks in English. And okay, small remark. So if you put the prompt like this in English to language model, it will work as well, of course. What was surprise is that it works that nice when you put the prompt in Polish. And but this is a language model, so we can basically expect that. So let me follow it and show the one of the first programs that I wrote in that I did in the DeepSeek using this prompt. So this is the prompt, the original one. I just put it there. There is no date, unfortunately, but okay. If we put a prompt like this into the web interface, you probably have seen that already. There is a thinking process going on in the background. What this thinking process is. So if you read it, I think nobody read it really in details, but if you go through it a little bit, you will see that this language model is able to recognize the main things from the knowledge that is in its network. So basically, it knows that this is lattice Boltzmann because it is selecting one of the most popular models, like the 2Q9. It's two-dimensional model. Okay, it is summarizing what the user wants to have. So for instance, what are the parameters, what is the grid setup, what are the initializations, and so on. Of course, we didn't put any details about what are the details of the numerical procedure. So for instance, GUO forcing is a standard method for incorporating external body force into lattice Boltzmann, which this network, this language model is getting from the literature, from the knowledge, and step by step it is formulating the problem in terms of mathematical description. So there is the equation for the transport and for the transport and collisions of the distribution functions of lattice Boltzmann, pretty standard for people from the field, and so on and so on. Here are the macroscopical values of velocity that are calculated from the distribution function. There is equilibrium distribution function from Maxwell distribution function, Maxwell distribution, and so on and so on. If you go through this, you will basically read like a book. But the book is a little bit of guided by our prompt. So it is like that. So it is filling these gaps, okay, that we didn't put, and so on and so on. And then at some point, the development of the code starts, and this is here. So basically, the parts of the code are written by the language model, and then at some point, let me go to the main part. This is the HTML file, which has the full complete lattice Boltzmann code written in a single code in JavaScript. Okay, I don't go into details, but of course, if you go more into details, you will see the equilibrium distribution function here cut it at some point, and so on and so on. Now, this is possible to just copy the code and run, but you can also do in the web browser. And now this is the result that I've seen in January. So when I've seen that, I was pretty amazed that it was so quick and without any errors. Because usually what we think is that these language models are making an error immediately, that there is some kind of we call it hallucinations going on. So if you hallucinate in code, then you are making huge mistakes probably, and then the code would not work. Here the code is pretty nice. I mean, working well. We see the standard Poisson profile. So the high velocity is in the middle and low velocity is on the top and bottom side. I don't know how many of you are from the fluid dynamics know that from the fluid dynamics perspective, but it is a very standard problem, and one can now ask more questions like check me the conservation of mass, please draw the plot of the velocity profile, adjust to the theory to see whether this is parabolic, and so on and so on. But I'm showing that because if there is anyone who didn't try the chat for for writing a software in this way, then you may be a little bit amazed how that this is how I was in January. But okay, let's say you already tried this, so you know that those chats can basically create software for you. So if it is so, then we can follow because then I have some ideas to show. So what I was trying to do, basically, I was also putting some particles in the flow, so that basically by another prompt. So that was the obvious idea that I asked for the program. Then I ask, okay, so please add me some particles so that they flow over the sorry, obstacle that is in the middle. So what you can see here is the flow over obstacle with particles going around. Then some of the particles were basically captured on the in the region where the solids were. Then I ask, okay, so remove those that have velocity equal to 0, and so on and so on. Doing like this, you can basically go deeper and deeper into your idea, develop the idea. So here, for instance, I was computing the tortuosity. That was my obvious thing that I wanted to check whether these programs can do what I was doing in the past. That was the very easy methodology that I had because I already knew what results I want to achieve. And then I started digging more into this tortuosity. And the idea was to check if these chats are able to compute what I was doing during my PhD. So here is the result of a paper. I will just show the paper to you. This is a paper from 2008. It's a paper about tortuosity, and I was computing a flow over systems of randomly deposited obstacles. So here you have a solution from lattice Boltzmann code, one that I was writing when I was PhD student, and these are the streamlines of a fluid going through narrow passages in between of a porous domain. And so there is a lot of things that I could tell you about this particular project, but one particular thing that I was computing was what is the tortuosity, meaning what is the elongation of those paths in a statistical manner. So I was computing statistically what is the elongation of a fluid paths in a function of number of those obstacles. Not really number, because I was computing porosity, okay? And then I could plot function that tells you what is this tortuosity in function of a porosity, and the results is here. So this is this on the x-axis you have porosity, means that if porosity is 1, there is no obstacles at all. If porosity is around 0.4, let's say 4.5, then there is so many obstacles that we are close to the percolation threshold of the system. Now, for each of this porosity, I was selecting some configuration of obstacles and computing the flow. And from this flow, I was able to compute how much wiggle it is. So the larger tortuosity, the more wiggle it is. So for instance, for porosity equal to 1, where there is no obstacles, the fluid flows on straight lines. Okay, and this is the result. So those x points are from a numerical procedure, sorry, and this line is empirical from experiment. And okay, this is the result that we got. And it cost me around 1 year to get it, where the development of the code was like 2 months, and then I was tweaking with it, doing this for larger grids and this and that. It was really difficult to get it because it is not that obvious what happens close to the percolation threshold and so on. Then I was close to this idea that I have a chat generated lattice Boltzmann, which was, I'm sorry, just this one prompt. It took me, I don't know, 3 minutes to write it down, and then 3 minutes to generate, and then 1 minute to run and see I have Poisson flow. Then I asked to do some more obstacles and so on. It took me a little bit of time. It is not like just a minute, but then I wrote this prompt. This is a result of a week of work. Okay, it was a week because I needed to develop it into a point where it will be complete and give a proper result. Now, why this is a single prompt? Why do I have information about the right simulation of lattice Boltzmann in periodic boundary conditions, accelerated by gravity, with particles? Then there are some details. I just make it bold where something important is there. So during computation, calculate tortuosity from velocity field, because there are two ways of computing tortuosity. Yes, two most standard. I selected one. I didn't have to put information about equation here, although I could do that. But if you know anything about tortuosity, then you know that if you compute from velocity, there is a particular equation to use. Now there is some details about the user interface and so on and so on. Remove particles that hit obstacle, for instance, and so on. There is some steady state condition to be fulfilled, and then there is something interesting because I can interact with the simulation and, for instance, add a button to randomize configuration so that there are obstacles and sliders to vary porosity and configurations and so on. And there is also, I'm sorry I didn't bold it, but there is information: please put randomly scattered impermeable obstacles of various shapes and similar sizes and so on. And this is a result. So this is an application that is created by the single prompt like that. And now I will explain you how did I get into this single prompt. So initially I created this Poisson flow, then I added particles, then I added obstacles, then I added the external force, then I added tortuosity computation. Then something wrong was with the simulation. I had to get back into lattice Boltzmann. But then when I started developing some tests and trying to tweak the numerical procedure somewhere inside of the code with the chat, it was ruining the other parts. So the system was not capable to keep what it has and just make another steps in the places I wanted. And it was way more efficient to create one single like a query prompt that was doing everything from a scratch. And then I didn't even use the same chat instance. I had to run it again and again from the very zero condition, and finally I get this. And I think if one has a prompt like that, it has a value, because with the prompt like this, not only a language model but also a very good student, your collaborator, someone who wants to repeat the results from the papers that you wrote can use the prompt like this to know and understand what is happening, what are the conditions. And I think if the summary like that was given in standard computational physics papers, that would be a lot of more useful for us than digging in the details of an articles that we are reading and trying to grasp the idea how the algorithm was formulated really with all the details. Because
Maciek, I have a quick question. How repeatable is this outcome? Because okay, you have written this prompt, I don't know, in 2024 or 2025, in September, whatever, on a particular chat, and then if I would like to use such exercises with the students, I would like them to, I would like to be able to predict what they see. And my own experience with chat is that, one day I ask him about something and he answers like this, the other day he answers little bit different. It's not hugely different, but little bit different. So my question is, is it like a normal code that once you write it, it is exactly this outcome, or is there some variability, involved in that?
it okay, so in I now I give you opinion because it's not something I can give you a proof for, but it all depends on the way you write the prompt. And sometimes if you write it on the high level of abstraction, like please write the simulation of lattice Boltzmann, then it can give you the lattice Boltzmann in D2Q9, but it also can give you D3Q15. Why not? It all the decision of the random process of the language model. But if you specify for this little thing, like the decision whether this is 2D or 3D, if this so write simulation of lattice Boltzmann in 2D, then it will not change it. It cannot change it. So you see, if you see the differences in running the prompts in different language model, then and you know what those differences, what are the meaning of those differences, then you can specify more deeper in the prompt that you want to keep. For instance, the I don't know the specific model of lattice Boltzmann written. So more details you give, the more specific result you will get. That's my answer.
Okay, thanks.
And then what I recognize from the because you were asking about the time differences. Yeah, you're right. During the year, we had like 5 or 6 versions of ChatGPT. Also, DeepSeek already has a new version that you may not have noticed because the DeepSeek is not announcing this. This is very funny. They are releasing very strong updates, but they are not doing what OpenAI is doing. They basically put it on the website, and now it's a newer one. And step by step, all those language models are developing. Of course, from the technical perspective, if you get a plain language model and you don't put the knowledge into language model, it will not create you lattice Boltzmann if you don't give all the details. So that's all we are in very rich environment with that. It's a very deep question you ask. But specification of the prompt is the first thing that you have to keep in mind. So one can ask students to basically run the prompt that he has on different language models and do the study like that, which is interesting, very interesting itself. I would say that's ready to do. I mean, very nice project to do. One can take a very strong prompt and then verify in different language models. It's actually a very nice idea. Okay, let me go on. And this is the program, so I'll just open it. Yeah. So this is the two-dimensional one, and so this is a flow. You can basically play with that. This is pretty standard. You can get it by doing the prompting like I showed you. But what I liked about it is that I can basically play with that. So I can change the porosity, for instance, randomize and take tortuosity. So even by hand, I can take I took the too large external force, so it will probably stop working in a moment, so I decrease this force a little bit, but increase the particle delta time. So I get to tortuosity. So for instance, here step by step I can change the porosity and calculate tortuosity for different conditions. Yeah, so you see those values are changing. They probably go in time. They change the so for me this is amazing because I spent a moment on creating a code. So now you see it was too much of the external force but too low porosity. So it's not a like wrong code. It's a typical for Lattice-Boltzmann to do stuff like that. So one has to know what he or she is doing because it's anyway the same numerical method. Yeah. But now what I did with that was I didn't dig more into the Lattice-Boltzmann itself, but I created another one which was computing tortuosity for like the same conditions like in the paper. So what you see on the plot here, it's the result of like 2 weeks of work where I repeated the results from my PhD, which are the red points on the curve like that. So you have the y-axis is tortuosity, x-axis is porosity. And I didn't really put a lot of effort to make them like this. I just knew what are the conditions I need. And the prompt I gave you with some little differences because I had to write a program that can do statistics on top of it, was able to repeat it. So for me it was amazing because I really didn't spend much time on it. I didn't put any specific knowledge, that just I knew what I wanted to compute. So I show this result very often to show that those charts are now very strong. And yeah, I didn't program a line of code. Okay.
But isn't it that, yeah, maybe that's the thing you want to mention now, the limitations, but isn't it so easy because you already know what you
Thank
want
you
to
for
get?
this question, and let's go on because this is exactly what I want to talk about. So my question was in the mind I was asking the same you asked. What are the limitations? I obviously didn't stop at Lattice-Boltzmann. I did that and that, of course, playing a lot. And then I was asking, okay, but is it there any limits, like whether I can do something that I never done, or something that people really are not that much doing? Because what is here now today is pretty standard. The flow through the pore scale flow with Lattice-Boltzmann, nothing special. I mean, I like the result, but it is like two-dimensional Lattice-Boltzmann, low velocity. Yeah, it's nothing really very serious. Okay, it is, but limitations. So I was asking, okay, let's do something crazy. And now I will show you the crazy stuff, a little bit crazy, that I was not digging more. Okay, so I'm sorry for doing that in a not very scientific way, because I obviously the first question will be what is the what are the whether all the conservation laws are fulfilled and so on, but what are the specific accuracies on the border of a very complex boundaries. But I was trying to do something crazy, like, okay, let's rotate the obstacles. I was like, this is very hard, especially in Lattice-Boltzmann. If you have an obstacle, you want to rotate it and see what is the flow around the obstacle like this. And funny thing was that I didn't even put a. I mean, here is a little bit of tweaking because the language model was giving me the initially some very bad results even visually they were wrong. But here I was interested whether I can run simulation like this. Okay, that was really the point, not to calculate anything serious. Don't get me wrong. Okay, I spent a minute on that. I wrote make them rotate, something like this, because I had three obstacles. And for me, as a person writing software like this, usually and playing with models to do stuff like that, it was amazing that it works. And from the thinking process, I see that the language model is able to find in the literature methods to basically to do the coupling of a rotating obstacle with the flow. It is using specific interpolation methods to interpolate the forces and velocities, coupling of the velocity. This is one-way coupling, so the flow is not influencing the the obstacle, but the obstacle is influencing the flow. And if you look here, you will see those saddle points here, for instance. So you have a flow in this direction, in this, and in that direction, okay? And so one can get something like that and start studying it. It is a lot of possibilities, okay? But let me go on because that's not the main point. But this was like a crazy stuff I was trying to do. Then I was okay. So how about 3D? Because three-dimensional tortuosity even. I'm sorry, this is not the. This is the code. So three-dimensional tortuosity is not really very much like investigated in the literature. If you ask the language model to give you the same solution but in 3 dimensions, then you basically get it, and it works pretty nice. This is a code created by the language model. I was even trying to, so if you increase porosity, it looks better because you basically can see the flow over individual obstacles. So let's wait a little bit. So those particles will now flow over obstacle. If you look carefully, you will see that there are particles going around. Okay, and from this you can compute tortuosity. And you know, a year before, I would say if I got a student who would be able to do this simulation in 3D and compute me tortuosity versus porosity in three-dimensional system of overlapping quads, then we would quickly write a paper because it was not done. The system like that was not investigated. And I'm not sure what is the three-dimensional plot of this function that I was doing during my PhD. But now this is like 5 minutes of work because I just wrote a prompt like that. And I get a program that gives you the answers. Of course, one has to validate and check and verify. That's all true. But this can be also done with the language models, okay? So that's the thing. Now let's move on. I was thinking of, okay, let's do something that was not really done. I mean, not numerically, as I know. And you know, my subject is tortuosity very much, so I know a little bit about the literature. Don't get me wrong, if you find a paper that study numerically with Lattice-Boltzmann non-overlapping obstacles, then you are, of course, I'm very happy. But I think there is no one. I mean, there are some theoretical papers about tortuosity with non-overlapping obstacles. The idea was that we take the same two-dimensional model, we basically put them, those obstacles, in some separate distance, so they separate with some constant. They create like a lattice, quite regular one. So the obviously porosity is limited. You cannot go towards the percolation threshold because the system like this has no percolation threshold. It has additional constant which is the distance of those particles. And I created a program, and this will show you more how complex is that, because now the program like this shows you even the tortuosity in time, so you can see how it develops in time. And just increase the delta time of particles so you see the flow, and you see how tortuosity changes in time, okay? And then at some point you can click add result, and you do the same for different so you basically randomize, and you do the same for different random configuration. But then we can put minimum distance, you see, so I can do the same but basically for minimum distance model. And for that, I can also see the tortuosity is converging to some point. I can add the results and do this many times for different. So this is the program, okay? But this program itself is not interesting. We have the results already. So I computed the same, but for the separated obstacles. And the result is pretty obvious that I got the lower velocities of tortuosity because the flow is no longer that wiggle, sorry. And those blue points are also results of the AI generated code. There are those AI generated code repeated for the overlapping the obstacles. The system has no percolation threshold, but I cannot go under 0.6 something because of the limits of the model itself. But it is interesting that the relation is linear. So this linear relation is known in literature. So people are calculating this theoretically. I even gave it a little bit of time to derive the theoretical theory for that using LLMs, but this is a different story, really, to understand and to really go through the theoretical derivations that you get from the language models. It is different. Here, I was working with AI generated code, and this is a result. It's not published. I didn't publish it yet. Don't know how to use it in science really. There is probably some new methodology that we have to use to show the people the results that we get with codes like that. But it is interesting because it gives knowledge already. Yeah, I already know how differently it behaves, and I have some ideas why I cannot go further. So maybe the tortuosity porosity relation is like this because of the percolation threshold itself, and then it would be different if we took out the percolation threshold. So the system would be infinite, yes? Okay, but now, is DeepSeek the only choice? There are some problems, technical problems with DeepSeek, that the server was busy very often. Yeah, if you tried it, you probably have seen it that you cannot go with many prompts because it stops working for you. It is better in now at the end of the year, but we also have ChatGPT, and not only, many other like Claude, Gemini, Grok. Be aware that Chinese language models like Ernie or Quen, they have something very specific in the AI, in the policy. So those two, and maybe even more, because there are more in the market. I didn't put. With all of those I was working, but Ernie and Quen do not give you. They don't give you rights to use it in commercial work, for instance. I didn't use commercially really yet, but it is interesting because the policy of GPT-5, Claude, Gemini, Grok are different from those two. So be aware. But anyway, what is interesting is that ChatGPT, the most known from the market, from the newspapers, has released deep thinking just 6 or 7 days after DeepSeek. So DeepSeek revolutionized the market and the AI because it was really very bad. The GPT-5 was, I mean not 5, but GPT was very bad in coding before the deep thinking processes were introduced. Those that are really doing many iterations back and forth. This was the originally released by DeepSeek, but what the message here is that probably it was there in OpenAI anyway before. Who knows what is now here today? We don't know. Let me now give you a little bit of advertisement. So what I was doing was I was writing a book. Once I was told that if you want to dig to something, you have to basically write about it. And I had a vision years ago that I want to write a book about modeling, because I give classes to students about modeling of in physics, in maybe a little bit of biology, chemistry, all those simple models that you know from the many courses. So in computational physics, you can basically solve partial differential equations, but you can also model systems by some agent modeling or by solving the cellular automata problem, and so on and so on. So I wanted to write a book about it years ago, but the problem I had was with time. Because if you want to make a book about many different models, then I was coding many of them. But to make them really well done and really like for each particular model to write an implementation, it is years of work. So then I had all this idea was in my mind, and then in January when I got this DeepSeek, I've seen it. I was like, wow! Now I can basically do it. I can take each of this model, implement it, and play with that, and basically go one by one. And then, because of all these research objectives that I had before with tortuosity, I came up with an idea that it has to be a single prompt written text. Otherwise, the reader would be lost because you are not able to go through the like many dozens of different different prompts, especially regarding to the question of Piotr, that once you run it on one language model, then on the other it will run differently. Then your second prompt would be a nonsense if the result was different. Then the only way to provide knowledge in terms of prompts is to provide a single prompt. And this is the title of the book, because it already I'm at the finishing process of writing it. So the what I did was to give a set of prompts for different models with detailed description of the algorithm, where the description is really low level. So basically each chapter is like a detailed description of the algorithm, so that it is not about each of the elements, because it's not possible. About the lattice Boltzmann, you can write a book, but you can also summarize the most important stuff in the lattice Boltzmann in a short, prompt way of writing. Actually, lattice Boltzmann is a bad example, because in the text I have, this is the most high level prompt I gave, because of what I know, it's not necessary to put all these details. But for the other models, I very often give a lot of details. I see I still have like 10 minutes. Okay, so some of those prompts or queries were taking me like a week and even more than a week of work. Some of them were really frustrating. This is not like I take a model and write a simple prompt and then it works. It is not possible. You have to test it in different language models, of course. Also, very often you get a result, but it is like fragile. Sometimes it works, sometimes it's not. And sometimes it gives you a good answer, but the user interface is wrongly created, like it covers half of your very, very simple technical stuff. It was like that. So it was a step by step making it more and more precise. Yeah, I'm like not very happy with all of them. I'm happy with some of them. With some of them, I'm like just by, not by accident is wrong word, but by not luck is also wrong. I at some point got a nice and good result, but I had to really spend more time to get it more robust. Okay, then what I just from the experience I got working on that, I would say these language models are like book to zero. They have a lot of knowledge and they give you even a way to get this knowledge and put into practice. And especially for me and maybe for us, if there are some computational physicists, as I know there are, this is a really strong tool, because now we can basically yeah, use it. For instance, the here is the single prompt from the book. This is basically how it looks in the book for a specific model. This is a prompt number 15, Ising model, typical standard Ising model. Okay, it is so you can read. It is like write a program in single JS file. Following the model, we are working on the array with periodic boundary conditions. Fill the array with +1 values. Randomly select one. So this is the typical Ising model. I will not go into details. There is some additional task. Add a button, and this is interesting because from the research perspective, one has to basically be able to do statistics. This is similar to what I did in Tortuosity. Add a button that add current properties to the text box where the results are stored in the form, blah, blah, blah. And then you can basically, at the end, I add a draft graph button that draws the values from the text box in separate graph along with the line drawn theoretical solution of the Onsager function. So it can even do the proper fitting of the theoretical functions to the results that you get. And then the result looks like this. I can run this for you. This is the Claude Ising model. And I basically, so this is one of the results from the book. So you get the magnetization in time. You can change the temperature. It's pretty standard, one could say. And you are right. what I recognized by doing this prompt, the 15.1, okay, there is, okay, I can add result, and it's not yet there. The result appeared in the result storage, but I can draw and then see that the result is here. It's not very nice because the resolution is not high. One has to do the resolution higher, and then this gets a little bit better. Okay, and I did it for the book. It looks like this. So we basically get the drop of magnetization with temperature. There is the phase transition and so on. And oh, sorry for the polish here. Anyway, so this is not a very good example, because the Claude, the one there was the Claude 4.1 on Opus, has recognized that this is Ising model. Then funny thing is that I was writing this algorithm, but I could probably even skip it because it's very typical Metropolis algorithm, and I could skip it and just write an Metropolis algorithm for it, and it would probably provide a very similar code. But if I change something in here, for instance, beta to beta square, I don't know, I'm just kidding, but if I put anything here, like another function for the temperature probability, then this language model will adapt the whole algorithm to the change that I gave. So it's not like the copying only. It is like very wise copying. This is why I call it like a Stack Overflow to zero, because this is what the IT people very often were doing. Programmers were copying from the Stack Overflow, which was the how this portal has developed. Now we have this knowledge somewhere, and we can use it and adjust a little bit. Okay, so let me follow, because that was the question I had at some point, whether there is possibility that to do something completely new. Like I take a model, because many of the models I have in the book are standard, but then I was asking, okay, so let's do something new, like a model that do not exist in the literature, the one that I put one by one the algorithm. And it is not very complex to, as I think the master student would basically do it without any problem, the one that knows how to program. But let me just describe you the model in very shortly. This is very simple. So in the there are those ballistic the deposition models like DLA, diffusion limited aggregates. And the DLA is, obviously it is in the book, but it is very standard. So you have a particle that goes in random movements and attached to the seed. But let's do something else. Some time ago I was thinking about model like this, and then with the language model I spent evening to basically have it done. Just of course I could program it, because as you know I'm programmer. I still are, I hope. But yeah, the idea was that we deposit particle on the somewhere around the seed. So we have a seed inside, and we deposit a particle and we shoot towards the center. So we basically shoot toward the center, and if you hit the cluster in the middle, then it attach. Then you shoot from another random angle. Then you shoot from another random angle, very like shooting the particles from around. The idea was, I don't know, I came up with that. That was like let's do Eden model different, okay? And I didn't know what will be the result. And then I got the result. So this is the ballistic model prompt. It is from the book as well. So it's much simpler even than Ising model. We work on a grid, we place an embryo in the center of the grid, we randomly select point on a circle. Yeah, but if you don't put all the details of this like procedure in the prompt like that, then the language model would be lost, or it would create the solution by itself. It would connect the dots by itself. So people call it hallucination. If you don't put the very detailed description, then you would get a model that hallucinates, that is filling the gaps. But here I knew what I want, so this is the procedure, then this is the result. And the result like this you cannot see in the literature probably, because nobody has came up with the idea like this. It's not very interesting idea really, because it's wrong. This was computed with Grok, and what I recognized is that the model is very subtle. I mean, it feels the grid. So you basically feel that going from the along the it is on the rectangular grid, sorry, on the square grid, and so those directions y and x are not special. Yeah, it looks nice. It has some beautiful structures, you know, from the deposition models, but because of those x and y directions, it is a little bit wrong. One has to do it either on the hexagonal grid or do it in a, somehow recognize why this happened, that you have those things there. But this was not the subject of my writing. The subject was to make it such that nobody has done model like that, so it's not copied. It is written, like programmed by the model, which is pretty amazing because this is randomly chosen words, yeah, for the code, as you know. This one was done with the Grok, but it works in each language models. And now, so the summary is that I have like 64 models for the whole text, and one of them is like smooth particle hydrodynamics, which costed me a lot of time, and the specific one was granular material with static friction, which took me like 2 weeks. And the professor that came to Wrocław to visit me for the conference has given me a hint while I was talking to him what I'm not aware about in the static friction model that helped me to make the proper prompt. The reason I was not able to get it done in a week was that I didn't know one subtle thing about some kind of the orientations of the forces in the static friction model, which is not really easy. And in the papers, it's not, I wouldn't say well described, but it's not detailed enough to be able to write it down in a natural language. So my thinking now is that once you can write down your model or application or algorithm in the natural language in a way that people will understand it, then the language model will understand it as well. So let me summarize. I have 3 minutes to summarize, so it's not the timing is there. We are dealing with something new. I think, and this is bigger than this seminar, but let me put a little message like that we have kind of paradigm shift in programming, because I think that I was programming for 25 years already, or even more, and I think I don't really need to program that much, because now many things, especially for prototyping, are like if I know what I want, then I can basically ask about it and just get it, and it's very nice, because then you can basically do it faster. But it's also yeah, it's a philosophical question whether we want to speed up or not, and I'm on this side that do not want to speed up. But anyway, let's leave it. Instead of assembler, C++ or Python, you can use natural language. I don't know how about all the other languages that are more that are, I mean, these are like structural languages, the objective ones. I don't know how about all those that are more complex. This is a big question. I would put one rule after the whole 7 months of work, was that there is a kind of LLM rule that one can say. The model will handle something if this is feasible. So if this is doable, then it will be done. If it's not, it will be hallucinated. That's it. So if you ask a wrong question, you will get hallucinations. I mean, one can call it hallucinations. One can call it filling the gaps. One can call it discovery. And that's a very big thing. Okay, I was asked by Piotr, I don't know how about after this seminar, so we'll see, but maybe there will be chance to meet me on University of Warsaw to give some part of the, like 1 or 2 lectures on the modeling course of Piotr for 2 days, so we'll see in 2026. I also want to incorporate those things into the modeling course that I give here in Wrocław, because I also teach students here, and I'm pretty sure they will be interested. And if someone comes to Nantes in 2026, I am thinking of a poster for modeling porous media with LLM to show this tortuosity stuff there. And also I'm thinking of the fluid dynamics conference in Łódź. This will be more about the fluid dynamics stuff. Thank you for your attention. That's pretty much it. If you have any questions, I'm very happy to answer.